All right, welcome everybody. We are going to return to some transformations. Once again, this entire unit is on the transformations of functions, meaning taking an original function and then shifting it around left or right, horizontally, vertically, up or down. We looked at reflecting, which is flipping the graph over the x or the y axis. And if we just want to return to this slide right here, just momentarily, just a reminder to ourselves, okay, that we have three different types of transformations altogether in this unit that you are going to keep investigating over the course of the next year, really. Okay, this stuff comes up over and over again in grade 12 math. We've already looked at translations. Translations are when you shift a graph. So you take the exact same function, but you just relocate it somewhere else on your graph. We also looked at reflections, which are flips, like I'd mentioned. And finally, we're going to look at stretches. Stretches is what changes the shape of something. You're going to make a graph wider or narrower, or you're going to make it taller or flatter. Okay, so you're going to literally take a graph and you're going to stretch it across horizontally to make it wider, or you're going to stretch it vertically up and down and make it taller, or you're going to do both. So if we take a look here, okay, at what we are presently learning here today, taking a look at horizontal and vertical stretches, much like translations, okay, you can stretch horizontally across or vertically. So what I have here, okay, is I have a random graph made up of 4 line segments, and I've labeled the 5 main points as A through E. And on the very left, I have a table of values with those 5 points. I am going to take those points and put into a mapping notation, and that is going to give me the new graph in G. So stretches work a little differently. So let's just think about what we've learned so far when it comes to mapping notations. Okay, we've learned that everything around the x is horizontal. So what comes after the x is a horizontal translation. That hasn't changed. What comes after the y is a vertical translation. So having things after the x or after the y will relocate your graph to the left, to the right, up or down. The stretches in a mapping notation show up in front of the x or in front of the y. So once again, x, of course, is across. The x-axis goes horizontal. So everything related to the x value in the mapping notation is horizontal. Everything related to the y value is vertical. So the stretches come in front of the x or y. The translations come after, to the right of x or y. So we're going to not do any translations with this graph. Okay, eventually we're going to take all 3 types of transformations and combine them together, but let's just focus on stretches for today. So why don't we take a look at a vertical stretch? We're going to create a vertical stretch of 2. So if we have a vertical stretch of 2, what's going to happen is literally vertically, your graph is going to stretch up and down. So this graph is going to get twice as tall. So what we do is we haven't done anything to the x's, so let's, in our mapping notation, in our table of values, let's keep the same x values right here. And instead, okay, what we're going to do is just focus on the y values, plug in the y values into the mapping notation, and if you do that, you're just timesing all of the y values by 2. So 4 times 2 is 8, 0 times 2 is still 0, and so on. If we plug in each of these y coordinates into the mapping notation, multiply by 2, you end up with these 5 new points, which I'll call A prime, B prime, all the way through E prime. And that's what we have right there. And then what we can do is we can graph each of these. So we're going to have E prime up here. D and B remain at the same places. But you can see right here that C is at 0, 4. And A is at -6, +8. And our new graph looks something like this. Okay, so you can see right here that if you do a vertical stretch of 2, you take the same function, you're not shifting it left or right in this case, we're not reflecting it around the x or y axis, We're just taking the graph and stretching it vertically twice as much. And if we were to make an equation from this, okay, this is how the equation would work here. So we would have our new function that we just created, which is g of x, is some version of our old function f of x. If you have a vertical stretch, the vertical stretch would come in front of the f like this right here. So this would be the equation that matches up. Okay, let's switch things up. Let's do a horizontal stretch instead. So what I'm going to do right about now is I'm going to erase some things that are going to be different. So I'm going to take my x and y coordinates for my new graph and switch those up. So we're going to have something like this right here. So let's get rid of all this. We'll keep f of x the same. Okay, f of x is the original function that I have there. So we definitely have these 5 points still. I'm going to get rid of this equation because we're going to have a new equation that matches our new mapping notation. But if I have something like this right here, okay, I'm going to switch things up a little bit, and I'm going to do my horizontal stretch. And this time, your stretch doesn't have to be a whole number like 2 or 3. If you look at this graph, okay, I don't really have room to stretch it across horizontally twice or 3 times as much. I need a lot more room on my graph paper. So what I'll do instead is I'll make my horizontal stretch a half. So what that actually does is if you're only going half the distance across, we're actually going to squeeze this together horizontally. It's going to be half the size apart. Like if you look at the beginning at A to the end in E, that is a total of 12 units from left to right, from the very left to the very right of this graph. So if there's 12 units horizontally, then if my stretch is a half, I'm going to shrink it down to 6 horizontally. We're going to see that happen in the mapping notation anyway, okay, and our new table of values. So let's do this, all right? So first of all, in this case right here, we're not touching the y values. So I'm going to keep the y values at 4, 0, 2, 0, 4. And what I'm going to do is I'm going to take the x values and I'm going to shrink them up. I'm going to times them by a half. Getting half of each of these numbers would look something like this right here. And if I plotted each of those points, all right, what I'm going to end up having here is I'm going to end up having negative 3, positive 4. So I have A prime right here. I have B at negative 1, 0. C at 0, 2, that hasn't changed. D at 1, 0. And E at 3, 4. And my graph now looks like this right here. And you can see that vertically it's the same height. It's still 4 units from the bottom to the top. But horizontally it's only half the size of the previous one. And that is a horizontal stretch as well. Even though you're not stretching, you're actually shrinking, okay? But the stretch is never going to be negative, all right? If there's a negative in front of a horizontal or vertical stretch number, it means that it's actually a reflection. And then when we make our equation here, something different happens here. Okay, what we do is when it's horizontal, we don't put the horizontal stretch in front of the f in the equation. That would be if it was a vertical stretch. In a horizontal stretch, it goes in front of the x. But what happens is all the x values change. So what we're going to do is if we have a horizontal stretch in the mapping notation, we flip that number over into the equation. So this is actually a 2x. And this is our equation right here that matches up with this mapping notation.